All right, welcome to part 2 of today's lecture where we're going to be discussing, well, not explicitly gravity, but gravitational potential energy. So here we have a system that we are going to be using similar to what we'll be having in our problems. We have some ball and the earth. So before we get into our system, I just want to clarify that we are still using the approximation for gravity that we are close to the surface of a large circular body. And what that allows us to do is use the force due to gravity as equal to mg. So here, the system, again, as the objects we're looking at, we're going to have a ball and the earth. So the reddish pink lines correspond to the forces. So we have the force of the earth on the ball and the force of the ball on the earth. And in the case of this ball in particular, it's been bounced off the earth and it is moving upwards. So when we are looking at it from some initial height yi to some final height yf. So if we wanted to look at the work being done on the ball, we would take the integral of the force due to gravity. So if we go through and look at our force, it's just equal to mg. There's no y value given. So when we take the integral, we're going to have mgy to the first power. And then we would need to plug in yi and yf, and we need to solve for the value for the work being done on the ball. I, of course, then immediately put that over text. Oops. Anyway, so we'd have this equation here where we have taken the integral. So again, we have m gy, yi to yf. So we've taken the integral, we've plugged in our values, and we've set it up. So the definition of the gravitational potential energy is it's going to be equal to mgy. So the gravitational potential energy is an energy of position. So based on where an object is located is going to tell us what the gravitational potential energy of an object is. Now there's something interesting about this particular equation. And that's because it's something that we've been doing all semester. And by doing all semester, I mean we've had the choice and we've used it a little bit, is we get to say where our origin is. We get to choose where y is equal to 0. So what that means is we can choose locations where the gravitational potential energy is equal to 0. So here we have two individuals. They're holding some meter sticks and there's a floating 1 kilogram rock. Let's ignore how the rock is floating in place, but let's focus on the coordinate systems that they've chosen. So Amber here on the left has said that the ground level is y is equal to 0. Whereas Carlos has said that where the rock is located is where y is equal to 0. So because of this, when we go through and we plug in our gravitational energy, so mgy, for Amber, y is 1 meter, the mass is 1 kilogram, and gravity is still gravity, doesn't matter who's looking at it. It's 9.8 meters per second squared. So 9.8 meters per second squared times 1 gives us our 9.0 or 9.8 joules. For Carlos though, m and g are the same, however y is now 0. So the gravitational potential energy would be 0 where the rock is starting. Now when the rock hits the ground, they would have the same change in gravitational potential energy. So when it's on the ground, Amber would have 0 because y is equal to 0. And Carlos would have negative 9.8 joules because we'd have mass of 1 kilograms times 9.8 meters per second squared times negative 1. So the change in gravitational potential energy is the same for both of them, even if the actual value itself is not. So when we do examples with conservation of energy, what we get to again on Wednesday, we'll talk about how to choose smart y is equal to 0 values. But typically, based on what you're choosing, gravitational potential energy is positive or negative depending on what you're picking. So a lot of people don't like dealing with negative numbers, so you choose a y is equal to 0 value such that you don't have to deal with a negative value. Now typically, and most common y is equal to 0 value is just put it on the ground or put it at the reference point. So maybe you're dropping everything on a table and the table is the lowest value a thing can go. So instead of having to always add the height of the table to all your values, just say the height of the table is equal to 0. So you can pick where y is equal to 0, and typically, again, we choose this in such a way that it is beneficial to us. Now, I don't know why this is here for energy bar charts, but it is. We're going to talk about it very briefly today. We'll talk about it again once we have the complete conservation of energy idea together. But basically what an energy bar chart is we look at the types of energy that we have within our system. So in this case, we're going to be dealing with a moving ball. So we're going to have kinetic energy, and because we're on Earth, some gravitational potential energy. So in the case of this ball on Earth, the ball here is on the ground, so that means that the gravitational potential energy is equal to 0. So here we are assuming that y is equal to 0, and technically, if we wanted to be really picky, y is equal to 0 at the center of the ball here. Now, if we wanted to consider the ball as a point, we would just say it's the ground. If the ball has a volume, saying it's at the center is technically the most correct. So this dashed line here corresponds to the idea that we have an ideal system. And what that means is that change in energy is going to be equal to the change in kinetic energy plus the change in potential energy, which is equal to 0. And right now, the only potential energy we're dealing with is going to be the gravitational potential energy. So as the ball moves upwards, we're no longer going to be on the ground, and we're going to lose some of our kinetic energy, and it's going to get transformed into gravitational potential energy. And we know the ball slows down because gravity is pointing downwards, the opposite direction of our velocity, which slows our object down. So that means that our kinetic energy, 1/2 mv squared, as v gets smaller, kinetic energy has to get smaller as well. Now, something about these two bars is if we were to stack them on top of each other, we would still get the same total energy value. And we can do that at the apex, or the top part of our motion as well, where we stop for a brief moment in time before we start moving downwards. Because we've stopped, our kinetic energy is equal to 0, and we have only gravitational potential energy. So it doesn't matter where we are in our motion, we have a constant energy value. And then as we move back down, oops, didn't fix that one all the way, the ball is losing potential energy and gaining kinetic energy until it hits the ground and we start the process over again. So this is a first look really into the conservation of energy, which says that the total energy is going to be, or the total change in energy is going to be equal to 0. So here we see that in a little bit more graphical representation of the kinetic energy changing such that the gravitational potential energy changes as well. And here we could look at this in terms of work if we really wanted to. But just as a hint, typically when we're dealing with conservation of energy, we're not going to be dealing with work. So let's not talk about it. All right, so let's go ahead and go through and do this example. So what I want you to do is pause the video, go through, and try to solve. So let's draw a very not to scale image here. So we have Mount Whitney, and we have Death Valley. So we are given, in this case, for our heights, we are given values based on sea level. So what that is telling us is that our y is equal to 0 value is sea level. Now we don't have to use this. We can use different values if we want to, and in fact we'll talk about those at the end. But let's solve using sea level as y is equal to 0 first, then talk about how those other ones would be different. So in this case, our initial position is going to be in Death Valley. So we'd be at negative 85 meters. And our final position would be at the top of Mount Whitney at 4,220 meters. So when we're looking at our change in gravitational potential energy, we'd have mg yf minus mg yi. So we could write this out as our 65 kilogram hiker times 9.8 meters per second squared, final position of 4,420 meters minus negative 85 meters. Taking this and plugging it in, I got 2856945 joules. Here I do have two significant figures for my answer. So I'd have 2.9 times 10 to the 1, 2, 3, 4, 5 to the 6 joules. This would be the change in gravitational potential energy for my hiker when I am going from Death Valley to the top of Mount Whitney. So let's talk about the other cases of where we can set y is equal to 0. So here we have, again, really rough image of what this looks like. So let's say that I wanted y is equal to 0 to be the bottom of Death Valley. Well, that would mean that my initial position is 0 meters. And the final position I have is going to be the 85 meters I need to get up to sea level, plus the 4,420 meters I need to climb Mount Whitney. So that'd be 4,485 meters. So the values overall end up being the same for when it comes to my final gravitational potential energy. It's just I needed to do a little bit more work with setting up my final height value. I could choose something like this as well, where the peak of Mount Whitney is y is equal to 0. So what that says is that my final velocity, or my final position, is equal to 0. Then my initial position is going to have to be the 4,420 meters I need to get down to sea level, minus the 85 meters below that. So it would be negative 485 meters. So again, I'd be starting at a really low gravitational potential energy value, and I'd be ending at 0. But the value I end up getting for any one of these y is equal to 0s gives me the same value for the change in gravitational potential energy. I could, not that I recommend it, do something really wild and say, well, the tree line is where I want y is equal to 0. I would need to know what the tree line for Mount Whitney is. I don't know what that is off the top of my head. So I would need to then scale both my yi and my initial and final position locations. It's doable. It's just not the smartest decision to do. So typically, and again, we'll practice this more with conservation of energy questions, we want to set our y is equal to 0 value in such a way that we don't have to change our numbers very much, if at all. So that's going to wrap it up for this video. Make sure to watch the third and final video where we're going to be looking at the other potential energy of this class, elastic potential energy.